Alrighty. Good morning, afternoon. I guess it's all morning, huh? Because by the time anyone in the afternoon will be at the pipe. So good morning, everybody. What I want to do here is go through this assignment and really kind of talk about what you need to do for each problem. Okay. So let's go here. Okay. So now we should be able to draw on this. Yeah, cool. Okay. It's been a minute. Sorry about that. So the first one, let's talk about the problem with the diver we did in class. So if you remember this problem, what it is there's a diver with a weight of 755 newtons. He is diving off of a 10-meter board. And what we did was we figured out what his final velocity was when he actually hit the water. But now what I want to do is I want to draw this line right here at 2 meters above the water, 2.00 meters. And I want to find out exactly what his speed is at that point. So again, I'm not going to actually do the entirety of the problem. I'm just going to kind of go and show you how it's done. So hopefully you guys have your notes. So we always want to start with mechanical energy initial equals mechanical energy final. That means that whatever mechanical energy he had when he jumped up off of the platform at the beginning of the problem, the energy of the system, he has to have that energy throughout the entire thing. And in your notes, you should have that mechanical energy is equal to the sum of potential and kinetic energies. So we're going to rewrite this as whatever potential energy plus kinetic energy he had at the beginning is equal to the sum of the potential and kinetic energies he had at 2 meters above the water. So the good thing for us is, if you're taking notes, you have all of this. The energy of the system is exactly the same. The first time, the problem we did in class was he was up there and he dove all the way into the water. Yay, splash. Okay. Now what we're doing is we're going, okay, instead of going into the water, we're going to draw this line right here. And we're going to say, okay, what's his kinetic energy at that line? So what that does is it actually adds right here. Okay. So this is still going to be his mass times gravity times height, which was 7,550 joules, plus his kinetic energy. That's 1/2 mv squared, which we figured out was 154 joules. So we know that the total energy of the system is 7,704 joules. And what we did to find the velocity was we just set that equal to his kinetic energy, knowing that when the diver hits the water, all of the potential energy has been used up and all that's left is kinetic energy. So here, though, we're 2 meters above. So we're going to go mgh. And remember that our mass times gravity is his weight, or 755 newtons. And we're going to put here the height of 2.00 meters. Now this part over here, 1/2 mass times velocity squared, that doesn't change. But what we now have over here is 1,510 joules plus whatever his kinetic energy is. Now, we already solved for mass. That should be in your notes. I'm not going to give it to you. And And then once we have that, we would subtract that 1510 from both sides. Shush, girls. And we would end up with whatever number this is right here, 6,194 joules, which is what represents his kinetic energy. And then we would just solve for velocity. Okay, so problem number 2. Stop. Okay, problem number 2, or in this case, it's really more like 1, 2, 3. Okay. And he's playing with yo-yo. Okay, so this is fun. And by fun, I mean it drives a lot of people nuts. So we have this yo-yo here, right? And it's spinning, 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 and then it falls some unknown amount, right? So here, this is the initial. This is the final. And we know that as it's traveling down here, when it hits this point, right before it goes and spins back up, it's going 1.9 meters per second. So that's going to be its final velocity. We know its initial velocity is 0, equals our initial velocity. So what this does for us is it allows us to kind of set this up as one of those stereotypical problems where all the mechanical energy at the beginning is potential energy. How do we know that? Well, because when we write the equations out, mass times gravity times height plus 1/2 mv squared, if we're not moving, then we don't have kinetic energy. And then on the other hand, where we have the potential energy at the end plus the kinetic energy at the end, there's no potential energy left because it has reached the bottom of the string. So this is just going to be that 1/2 mv squared. Now the trick here is if you were paying attention to the instructions, it says to solve for h. So when we have mass times gravity times height equals 1/2 mv squared, a lot of people who actually got this far on Thursday said, hey, hold on a second. We can't do this without the mass we can't figure out speed without mass. But you can, and here's why. I can divide both sides by m. Okay? Divide both sides by g. And this would give me h equals v squared over 2g. So notice that the mass doesn't have anything to do with it. So from this point on, you should be able to look at the problem and figure out how to solve for the height that it dropped, which is going to be equal to the length of the string. Okay. Moving on. See? It's all easy. The jack-in-the-box problem. Okay, so a couple things with the jack-in-the-box problem. First, notice that the mass you're given is in grams. It's 50 grams. The distances you're given, the heights, so to speak, are in 10 centimeters, or 2 centimeters. We are dealing with things like joules, which is kilogram meters squared per second squared, or newtons, which is kilogram meters per second squared. Hey, Fee. So the first thing we need to do is we need to change all of our units into the standard units, right? The kilograms, meters, seconds, so to speak. So 50 grams, we would move the decimal point 3 places. So that's going to be 0.050, I think it's 0 kilograms. 10 centimeters, we're going to move it back 2, so that becomes 0.1 meter. And 2 centimeters, we would move back 2 as well. So it'd be 0.02 centimeters. Okay. What's up, girl? So, when we're looking at this problem, we have this spring that's compressed, right? So it's normally that 0.1 meter. Now it's been compressed to 0.02 meters. And it's got a little head here that is 0.05 kilograms. So when we let it go, that spring is going to spring up, right? And we want to know how fast the head of the jack-in-the-box is going at the top there. So here, when we have potential energy plus kinetic energy, it's important to realize that we have 2 types of potential energy here. We have the potential energy of the spring, or elastic potential energy, which is 1/2 kx squared. And then we have potential energy due to gravity, which is m times g times h. So we're going to need to find the sum of our potential energies, which is going to be the spring potential energy plus our gravitational potential energy. Now, when we set up this on the other side, notice what's happening is because the spring is pushing it up, we're definitely going to have kinetic energy because the spring is moving, right? And this is ultimately what we're looking for here, that velocity. But we're also going to have some potential energy. And the reason that we're going to have potential energy is because, well, look at my pretty little drawing over here, right? Because the head of the thing moves up, we are going now to have 0.1 meters worth of potential energy with the jack-in-the-box. Let me erase that. So figure out how much total potential energy it has. Set it equal to the potential energy of 0.1 meter. We already know its mass, so we should be able to manipulate that to solve for its velocity. Okay, and again, try these by yourself. Work with other people. That's totally okay. And anything you can't do, we can take a look at on Monday. But hopefully this will give you kind of some guidance. So the last problem that we're looking at is really kind of a hybrid problem. And it requires a little bit of a throwback to the work kinetic energy theory, right? So we've got doing chin-ups. And we have, what was it, 355? Okay, so we have 300, so we have one arm here. So what we can really look at is kind of arm. This arm is going up with 355 newtons. This arm is going up with 355 newtons. Then we know the mass of the body is going to go down with, what was it, 700 newtons. Exactly. Okay, cool. It is 700.0 newtons. So first things first, we need to find the sum of the forces. Okay? You should be able to look at this and figure out that he is moving upwards with a limited amount of force. We also know that he raises himself 25 centimeters. Now, if you're paying attention on the last one, you realize that one of the problems here is that I just wanted to go and check and make sure it was centimeters, or 25 centimeters, is that we can't have the answer, or we can't have any of our measurements be in centimeters. So what we're going to do is we're going to call this distance as 0.25 meters. Okay? We're going to figure out what the sum of the force is. We know that work is force over distance. We also know that work equals kinetic energy. And we know that kinetic energy equals 1/2 mv squared. So what's going to happen is we're going to find the sum of the forces. We're going to multiply that by that 0.25 meters. We're going to set it equal to the kinetic energy equation. We're going to have to solve for this mass. We know that the weight equals 700 newtons. But we need to figure out what the mass is. Okay? Sorry, just going to zone out there for a second. And then once we have the sum of the forces, multiply that by 0.25, get the mass, because remember, weight is just mass times gravity. We know that gravity equals 9.81 meters per second squared. So we know that weight is a force. Force equals mass times acceleration. Or that in this case, mass is going to equal force divided by acceleration. So as we get that, we know the mass of the object. We can plug it into this equation and then solve for our velocity. And I believe that's it, right? I think that's the last one. Yeah, that's it. So hopefully you learned something. And I will see you guys next week. Have a wonderful day, and I hope you behave extremely well for Miss Myers. Meyer, sorry. Good night, y'all.